I was sitting by my window earlier this evening, watching the sky slowly darken as the last amber light of sunset faded into deep blue beyond the rooftops. There is something about these quiet hours after twilight, when the first stars appear, that makes the universe feel strangely personal and close despite its vastness. A few faint points of light had emerged in the eastern sky, each one a distant sun burning steadily across impossible reaches of space and time. One of those ancient suns holds a story that puzzled astronomers for decades, and tonight I want to share its remarkable mystery with you. Before we begin this journey, I'd like to ask a small favor if you don't mind sharing where you're tuning in from tonight. Let me know your city and the hour, and if these quiet explorations help you unwind, consider subscribing so you can return whenever you need. Tonight we will explore one of astronomy's most curious puzzles, a star that once appeared several 100 million years older than the universe that contains it. You heard it right. We will also learn how astronomers measure stellar ages and how science eventually resolved this beautiful paradox through years of careful observation and refined understanding. The star we are discussing carries the formal designation HD 140283, number that reveals nothing about the remarkable nature of what it truly represents. Astronomers gave it a more memorable name, calling it the Methuselah star, after the biblical figure said to have lived longer than any other human in Scripture. In ancient texts, Methuselah lived 969 years, an unthinkable span. And this distant sun seemed to embody that same quality of impossible longevity. The star resides in the constellation Libra, roughly 200 light-years from our solar system, close enough by cosmic standards to study in remarkable detail tonight. When astronomers first calculated the age of this ancient star, the result proved deeply troubling because the number reached 14.5 billion years old. Our best measurements tell us the universe itself is only 13.8 billion years in total age since the moment of the Big Bang. This presented an obvious logical impossibility, because nothing within the universe can possibly be older than the universe itself, just as no child can predate its parents. Yet here was a star burning quietly in Libra, whose calculated age exceeded the cosmos by roughly 700 million years, creating a genuine scientific paradox demanding explanation. To understand how this puzzle emerged and how it was eventually resolved, we need to explore several branches of astronomy and physics, working together across decades. We will learn how scientists read information from starlight, decoding chemical compositions and temperatures from photons that traveled across space for centuries before reaching our telescopes. We will understand how astronomers classify stars into different generations, each born in distinct eras of cosmic history with different chemical signatures marking their ancient origins. And we will follow the patient work of researchers who refined their measurements year after year until the numbers finally began to align with cosmic logic. The Methuselah star first attracted serious scientific attention in the early 20th century, when astronomers noticed something unusual about its motion across the celestial sphere over time. Most stars appear essentially fixed in their positions relative to one another, but HD 140283 moves noticeably against the background, shifting its apparent location faster than typical stars. This rapid proper motion suggested the star was relatively nearby, not billions of light years distant, but merely a couple hundred light years from our solar system. The closeness was fortunate for astronomers because it meant they could study this ancient object in detail that would be impossible for more distant stars in the galactic halo. The star's velocity through space is remarkable, traveling at over 800,000 miles per hour relative to our Sun and the surrounding stellar neighborhood here. This extraordinary speed is not random, but tells a story about the star's origins, suggesting it was born in a very different region of the galaxy entirely. Stars born in the galactic disk, where our Sun resides, orbit the galactic center in relatively orderly patterns like horses on a carousel. But HD 140283 follows a highly elliptical path, diving through the disk on an orbit that takes it far into the ancient galactic halo above and below. The galactic halo is a vast spherical region surrounding the Milky Way's flattened disk, and it contains some of the oldest objects in our entire galaxy. Stars in the halo formed billions of years ago, before the galaxy had fully settled into its current structure of spiral arms and orderly disk rotation. These ancient halo stars are like archaeological artifacts, carrying chemical signatures from an era when the universe was young and elements heavier than helium were scarce. HD 140283 is one such traveler from that distant time, and its presence in our neighborhood gives astronomers a rare opportunity to study the ancient cosmos. When we look at this star through a telescope, we are not simply seeing a point of light, but receiving information that has traveled through space for centuries. The photons entering our instruments tonight departed from the Methuselah star around 1825, when Beethoven was composing and the Industrial Revolution was young. But the star itself carries information from far earlier. Chemical elements forged in the first billion years after the Big Bang, encoded in its spectral signature. In this sense, the Methuselah star is a messenger, bringing news from cosmic dawn to anyone patient enough to decode the ancient language written in its light. Tonight, we will learn to read some of that language, understanding how astronomers extract information about temperature and composition from the light of distant suns. We will explore the Hertzsprung-Russell diagram, a remarkable tool that maps the lives of stars and reveals where each sits in its evolutionary journey through cosmic time. We will discover why the earliest stars contained almost no heavy elements, and how this primordial chemistry serves as a timestamp from the very early universe. And we will see how improved measurements and refined physics eventually brought the Methuselah star's age into agreement with our understanding of cosmic time and existence. The story of this star is ultimately a story about how science works when confronted with data that seems to contradict everything we know to be true. Scientists did not ignore the paradox or dismiss it as measurement error without investigation, but instead took it seriously as a genuine puzzle requiring careful examination throughout. They questioned their assumptions about stellar evolution, about distance measurements, about the physics of nuclear reactions in ancient stellar cores, leaving no assumption unexamined. In the end, the resolution came not from any single dramatic discovery, but from the patient accumulation of small improvements in our understanding of stellar physics. Before we continue further, let me describe what we actually see when we point a telescope toward this particular patch of sky in Libra on clear nights. HD 140283 is not a bright star visible to casual observers, having an apparent magnitude of about 7, just below the threshold of naked eye visibility. You would need binoculars or a small telescope to see it, and even then it would appear as just another faint point of light among thousands. There is nothing visually spectacular about this star, nothing that would mark it as special to an observer unaware of its extraordinary history and cosmic significance. Yet this modest appearance is deceiving because HD 140283 belongs to a rare class of objects that have survived from the universe's earliest epochs of star formation. The overwhelming majority of stars from that ancient era have long since died, ending their lives as white dwarfs or neutron stars, or scattered completely. Only stars with relatively low mass, burning their nuclear fuel slowly and steadily, have the longevity to persist for over 12 billion years of cosmic time. HD 140283 is one of these survivors, a star that has patiently burned through the eons while galaxies formed and countless generations of stars lived and died. The star is classified as a subgiant, meaning it has begun the slow transition from its main hydrogen-burning phase toward the red giant stage of stellar evolution. This evolutionary state is important for understanding its age, because where a star sits in its life cycle provides valuable clues about how long it has existed. Subgiants have exhausted the hydrogen in their cores and begun burning hydrogen in a shell surrounding the now inert helium center, marking a specific phase of development. By comparing the observed properties of HD 140283 with theoretical models of stellar evolution, astronomers can estimate when this star most likely began its life in cosmic history. The surface temperature of the Methuselah star is approximately 5,700 Kelvin, surprisingly similar to our own Sun despite the vast difference in their ages and origins. This temperature places it in the yellow-white range of stellar colors, though its light contains subtle differences from the Sun that reveal its ancient nature unmistakably. Those differences are primarily in the chemical absorption lines, the dark bands in the spectrum where atoms in the stellar atmosphere have absorbed specific wavelengths of light. The Methuselah star's spectrum shows remarkably weak absorption from iron and other heavy elements, indicating a composition vastly more primitive than stars formed in recent cosmic epochs. This chemical poverty is actually the key to understanding why the star is so ancient, because heavy elements simply did not exist in abundance during the early universe. When the cosmos was young, only hydrogen and helium and traces of lithium had been created during the Big Bang, the primordial nucleosynthesis that shaped early chemistry. Heavier elements like carbon, oxygen, and iron were forged later in the cores of massive stars, then scattered into space when those stars exploded as supernovae. A star with very low heavy element content must therefore have formed early, before the cosmos had been enriched by many generations of stellar death and recycling. Astronomers use the term metallicity to describe the fraction of a star's mass composed of elements heavier than helium, even though most aren't technically metals in chemistry. The Methuselah star has a metallicity of approximately 1/200th of our Sun, meaning it contains about 200 times less iron and similar elements than our Sun. This extremely low metallicity is consistent with formation in the first billion years, after the Big Bang, when the universe was still largely pristine in chemical composition. The chemical signature alone tells us this star is ancient, even before we attempt the more complex calculations of its actual age in billions of years. Now we begin to see why the Methuselah star attracted such intense scientific interest, and why its apparent age paradox was taken so seriously by researchers worldwide. Here was an object with all the hallmarks of extreme antiquity: low metallicity and high velocity and halo orbit that seemed to predate the universe itself somehow. Either our understanding of how to date stars was flawed, or our measurement of the cosmic age was wrong, or both needed significant revision and improvement. The paradox demanded resolution, and astronomers spent years working through every possible source of error before finally achieving an answer that satisfied both observation and theory together. In the parts that follow, we will trace this scientific journey step by step, beginning with the fundamental techniques that allow us to analyze starlight at all. We will build understanding gradually, each concept laying the foundation for the next, until the full picture of the Methuselah paradox comes into focus clearly before us. There is no need to rush through this material, because the gentle accumulation of knowledge is part of what makes astronomy such a peaceful subject to explore. The universe has been here for nearly 14 billion years, and the Methuselah star has burned steadily for most of that time without any urgency at all. If you find yourself settling deeper into stillness as we continue, that is perfectly natural, because these cosmic perspectives often quiet the restless mind beautifully. The vast scales of time and space we discuss have a way of making everyday concerns feel smaller and more manageable against the grand cosmic backdrop. So let us continue at whatever pace feels comfortable, allowing the story to unfold as slowly as starlight crossing the void between distant suns and Earth. The Methuselah star teaches us something profound about the nature of scientific investigation and the willingness to hold conclusions lightly when new evidence emerges from careful observation. For years, astronomers knew something was wrong with the numbers, but could not immediately identify where the error lay in their calculations and underlying physical models. Rather than abandoning the mystery or forcing a premature answer, they continued gathering data and refining techniques until clarity eventually emerged from the patient work. This is the true rhythm of science. Not dramatic eureka moments, but slow, steady progress toward understanding, one careful measurement at a time, across many years. As we move forward through this exploration, we will encounter technical concepts explained in gentle terms, always connecting the details back to the larger story being told tonight. You need not memorize every fact or follow every calculation precisely, because understanding the broad shape of the narrative matters more than remembering specific numbers in detail. The goal is to appreciate how astronomers approached a genuine mystery and worked through it systematically, demonstrating the power of collaborative scientific inquiry across decades. And perhaps along the way, the quiet contemplation of cosmic time and ancient stars will provide exactly the peaceful atmosphere your mind has been seeking tonight. We have now set the stage for understanding one of astronomy's most curious puzzles, and the ancient star at the center of the story awaits our attention. The Methuselah star has been burning steadily for billions of years, and it will continue long after our brief examination of its secrets concludes in these hours. But in the time we have together, we can appreciate something remarkable about this faint point of light, a survivor from the dawn of cosmic history. Its light carries information from an era we cannot otherwise access, a time when the universe was young and stars were just beginning their existence throughout the cosmos. In the next part, we will examine the Methuselah star more closely, exploring its physical characteristics and the unusual motion that first attracted scientific attention to this wanderer. The star known as HD 140283 appears unremarkable through a telescope eyepiece, presenting as a faint point of yellowish light that would never draw attention without prior knowledge. With an apparent magnitude of about 7.2, it falls just below the threshold of naked eye visibility, requiring at least binoculars to observe directly from Earth. In the constellation Libra, it occupies an ordinary patch of sky, far from any famous nebulae or clusters that might attract casual stargazers to the region naturally. Yet this modest appearance conceals an extraordinary nature, because HD 140283 is one of the oldest stellar objects we can study in such remarkable detail from Earth. The designation HD refers to the Henry Draper Catalogue, a stellar classification project completed in the early 20th century that assigned numbers to hundreds of thousands of stars. The number 140283 simply indicates its position in that long list, a bureaucratic label that tells us nothing about the star's significance or its ancient origins. Many of the most important objects in astronomy carry such uninspiring names, catalogue numbers that reveal their place in surveys rather than their true, remarkable nature. The name Methuselah came later, when astronomers needed something memorable to describe a star that seemed to have witnessed the earliest chapters of cosmic history unfold. The position of HD 140283 in the sky places it in a relatively sparse region where few bright stars compete for the observer's attention on clear nights. Libra itself is not one of the more prominent constellations, lacking the dramatic patterns of Orion or the distinctive shape that makes the Big Dipper so recognizable. Finding the Methuselah star requires careful navigation with star charts, hopping from brighter reference points until the faint target finally appears in the telescope's field of view. For most of human history, this star went completely unnoticed, just another anonymous point among the millions visible from Earth on any given night throughout the centuries. The first astronomers to pay serious attention to HD 140283 were not initially interested in its age, but rather in its peculiar motion across the celestial sphere. In the late 19th and early 20th centuries, astronomers were systematically measuring the positions of stars with increasing precision, looking for any changes that might reveal distance or movement. Most stars appeared fixed relative to one another, their positions unchanging over human lifetimes because they are so incredibly far away that their motion becomes imperceptible. But HD 140283 was different, showing measurable drift against the background stars over periods of just a few decades, marking it as an unusually mobile object, worthy of study. This apparent motion across the sky is called proper motion, and it reflects the star's actual movement through space, combined with our own solar system's velocity. HD 140283 has one of the highest proper motions of any star visible in our region of the galaxy, traveling noticeably across the celestial background year after year. Early astronomers measured this motion at about 1.3 arcseconds per year, which may sound tiny, but represents unusually rapid movement for a star at this distance. Over a human lifetime, the Methuselah star shifts position by an amount visible through careful telescope measurements, slowly wandering across the constellation Libra through the decades. The high proper motion immediately suggested something important about the star's location in space, indicating that it must be relatively nearby compared to most stars in the galaxy. Distant stars show almost no proper motion even if they are moving rapidly, because the vast distance shrinks their apparent movement to unmeasurable amounts over human timescales. A star with significant proper motion must therefore be close enough for its actual velocity through space to translate into detectable angular displacement as seen from Earth. HD 140283 was only about 200 light-years away, practically a neighbor by cosmic standards, making it accessible for detailed spectroscopic analysis with the instruments available. But the proper motion revealed something else equally important about the Methuselah star, something that hinted at its ancient origins and unusual history within the Milky Way galaxy. The direction and speed of its motion suggested an orbit radically different from stars born in the galactic disk, where our own sun resides among the spiral arms. HD 140283 appeared to be plunging through our neighborhood on a highly elliptical path, diving into the disk from above before eventually swooping back into the halo again. This orbital behavior identified it as a halo star, a visitor from the ancient spherical envelope of old stars that surrounds the Milky Way's flattened central structure. The galactic halo is one of the oldest components of our galaxy, a roughly spherical distribution of ancient stars and globular clusters extending far beyond the visible disk. While the disk rotates in an organized fashion, with stars orbiting the galactic center in roughly circular paths, halo stars follow chaotic, elongated orbits in all directions possible. These halo stars were born before the galaxy had settled into its current shape, when the primordial gas cloud was still collapsing and turbulent. Conditions prevailed throughout. Their orbits preserve the memory of that chaotic era, carrying them on long loops that take billions of years to complete each journey around the galactic center. HD 140283 follows exactly such an orbit, spending most of its time far above or below the galactic plane, before briefly passing through our neighborhood on its travels. Its current position near the Sun is a temporary circumstance, a chance alignment that places this ancient wanderer within reach of our telescopes for a cosmic moment. In a few million years, it will have moved on, continuing its long, elliptical journey into the halo where it will remain invisible to casual observation. We are fortunate to live in an era when this ancient star happens to be passing through, giving us a window into the early universe through its light. The velocity of HD 140283 through space is extraordinary by stellar standards, exceeding 800,000 miles per hour relative to the Sun and surrounding stars in our area. This speed is not unusual for halo stars, which must move rapidly to maintain their elongated orbits against the gravitational pull of the galactic center's massive concentration. Stars in the disk, by contrast, move in more circular orbits at slower speeds, staying within the rotating plane much as cars stay in their lanes on a highway. The Methuselah star's velocity immediately identified it as a different kind of object, following different rules. governed by the dynamics of the ancient halo rather than the disk. This kinematic evidence for an ancient origin complemented what astronomers were learning from the star's spectrum, its chemical fingerprint revealed through careful analysis of its light patterns. Spectroscopy showed that HD 140283 contained remarkably little iron and other heavy elements, far less than the Sun and other stars born in the enriched disk of the galaxy. This chemical poverty, combined with the high velocity and halo orbit, built a consistent picture of a star born in the early universe when heavy elements were scarce. Everything about HD 140283 pointed to extreme antiquity, making it a prime target for detailed studies aimed at understanding the universe's earliest stellar populations and their characteristics. The star's physical properties can be measured with considerable precision thanks to its relative proximity, allowing astronomers to determine its temperature, luminosity, and surface gravity accurately. HD 140283 has a surface temperature of approximately 5700 Kelvin, placing it in the yellow-white region of the stellar spectrum, not far from our own Sun in color. Its luminosity is about 3 times greater than the Sun's, indicating a star that has evolved somewhat beyond the main sequence phase of hydrogen core burning. The surface gravity is lower than the Sun's, consistent with a slightly expanded star that has begun its slow transition toward the red giant stage of evolution. These properties together indicate that HD 140283 is what astronomers call a subgiant, a star that has exhausted the hydrogen fuel in its core and begun evolving off the main sequence. During the main sequence phase, stars burn hydrogen in their cores through nuclear fusion, maintaining a stable balance between gravity pressing inward and radiation pushing outward from the center. When the core hydrogen is depleted, the balance shifts and the star begins to change, with hydrogen fusion moving to a shell surrounding the now inert helium core. The star expands and brightens somewhat, moving off the main sequence toward the red giant branch, and HD 140283 is currently in this transitional phase of its existence. The subgiant classification is important for age determination because it tells astronomers where the star sits in its evolutionary journey, providing crucial information for calculating how long it has burned. A star spends most of its life on the main sequence, so reaching the subgiant phase indicates substantial age, with most of the star's nuclear fuel already consumed. By comparing the observed properties of HD 140283 with theoretical models of how stars evolve, astronomers can estimate when it likely began its life in the early universe. This evolutionary clock, combined with the chemical evidence, provided the foundation for the Person age estimates that would eventually create such a puzzling paradox in astronomical understanding. The mass of HD 140283 is estimated at about 80% of the Sun's mass, making it a relatively modest star by cosmic standards, neither large nor particularly small. This moderate mass is actually crucial for its survival to the present day, because more massive stars burn through their fuel rapidly and die within millions of years. A star twice as massive as the Sun might live only 1 billion years before exhausting its nuclear fuel, far too briefly to reach the age that HD 140283 has achieved. Only stars with masses near or below the Sun's have the longevity to persist for 10 billion years or more, slowly burning their hydrogen over cosmic timescales. The low mass of the Methuselah star means it has burned its fuel slowly and steadily, converting hydrogen to helium at a pace sustainable over billions of years. This patient nuclear burning has allowed HD 140283 to survive from the earliest epochs of star formation, while more massive contemporaries died long ago in spectacular supernova explosions. Those massive stars lived fast and died young, scattering heavy elements into space, but leaving no direct survivors for us to study in detail today across the cosmos. HD 140283 represents the opposite strategy, a low-mass star that traded brilliance for longevity, and in doing so became a precious window into the ancient universe for modern astronomers. The star continues its journey through the galaxy, indifferent to the attention astronomers have lavished upon it, following the same orbit it has traced for billions of years. It has passed through the solar neighborhood before, many times over the eons, though of course no human observers were present during those earlier visits to record its passage. And it will continue passing through long after our civilization has run its course, a patient traveler marking the slow rhythm of galactic time through its eternal wandering. For now, we are fortunate to have this ancient visitor within reach, able to study its light and learn what it can teach us about cosmic origins. The properties of HD 140283 that we have explored paint a consistent picture of an object born in the earliest era of star formation in the universe itself. Its high velocity and halo orbit indicate birth before the galaxy settled into its current form, when chaotic conditions prevailed in the collapsing primordial gas cloud. Its low metallicity confirms formation before supernovae had enriched the interstellar medium with heavy elements, when only hydrogen and helium were available for building new stars. And its subgiant evolutionary state indicates it has been burning for a very long time, long enough to have exhausted the hydrogen in its core already. All of these lines of evidence pointed toward an extremely ancient star, perhaps one of the oldest objects accessible to detailed study in our cosmic neighborhood today. This made HD 140283 an obvious target for precise age determination, using the most sophisticated techniques available to calculate exactly when this star began its life in the universe. But when astronomers performed those calculations, using the best data and models available, at the time, they encountered a result that seemed to defy logic and basic physics. The age they derived was impossible, older than the universe itself could possibly be, setting the stage for one of astronomy's most curious paradoxes in recent decades. In the next part, we will explore how astronomers read information from starlight, learning the techniques of spectroscopy that reveal temperature and composition hidden in the light of distant suns. When we observe a star through a telescope, we are gathering photons that have traveled across space for years or centuries before reaching our instruments on Earth. These tiny packets of light carry encoded information about the object that emitted them, revealing secrets about temperature and composition to anyone who knows how to read the message. The science of extracting this information from starlight is called spectroscopy, and it has been the foundation of stellar astrophysics for over 150 years now. Without spectroscopy, we would see stars only as points of light, knowing almost nothing about what they are made of or how hot they actually burn. The story of spectroscopy begins with Isaac Newton in the 17th century, when he demonstrated that white light could be split into a rainbow of colors using a prism. Newton's experiment showed that sunlight was not a simple uniform thing, but a composite of many different wavelengths blended together into what we perceive as white. This discovery was foundational, but it would be nearly 2 centuries before scientists realized that these colors contained far more information than anyone had initially imagined or expected. The hidden messages in starlight awaited better instruments and more careful observation before they would begin to reveal their secrets about the nature of distant suns. The crucial breakthrough came in the early 19th century when Joseph von Fraunhofer carefully examined the spectrum of sunlight and noticed something unexpected: dark lines crossing the rainbow. These dark bands appeared at specific locations in the spectrum, always at the same wavelengths, suggesting they were not artifacts, but real features of the solar light. Fraunhofer catalogued hundreds of these lines, labeling the most prominent ones with letters that astronomers still use today when discussing the solar spectrum and its characteristics. He did not know what caused these mysterious dark bands, but his careful measurements laid the groundwork for one of astronomy's most powerful diagnostic tools in later decades. The explanation for Fraunhofer's dark lines came from laboratory experiments conducted by Gustav Kirchhoff and Robert Bunsen in the 1860s, revealing the connection between light and chemistry directly. They discovered that each chemical element, when heated, emits light at specific characteristic wavelengths, producing a unique pattern of bright lines, like a fingerprint identifying that element. Furthermore, when light passes through a cooler gas containing that same element, the gas absorbs light at exactly those same wavelengths, producing dark lines instead of bright ones. The dark lines in the solar spectrum were absorption features, caused by atoms in the sun's outer atmosphere absorbing specific wavelengths from the continuous light emerging from deeper layers. This discovery transformed astronomy overnight, because it meant that the composition of distant stars could be determined from Earth simply by analyzing their spectral patterns carefully. Previously, astronomers could only measure the positions and brightnesses of stars, knowing nothing about what they were actually made of or how they functioned as physical objects. Now, each absorption line became a clue, identifying the presence of specific elements in the stellar atmosphere with the precision of a laboratory measurement from across vast distances. Hydrogen, helium, iron, calcium, sodium, and dozens of other elements could be detected and measured in stars light years away, revolutionizing our understanding of stellar composition and chemistry. The sun's spectrum is crossed by thousands of these absorption lines, each one corresponding to a specific atomic transition where an electron jumps between energy levels within an atom. When a photon with exactly the right energy encounters an atom in the stellar atmosphere, it can be absorbed, exciting an electron to a higher energy state. This removes photons of that specific wavelength from the outgoing light, creating a dark gap in the spectrum at that particular color where absorption has occurred. By measuring the positions and depths of these absorption lines, astronomers can determine not only what elements are present, but also their relative abundances in the atmosphere. The temperature of a star also leaves its mark on the spectrum, affecting which absorption lines are strong and which are weak or absent altogether in the pattern. At high temperatures, atoms are more likely to be ionized, with electrons stripped away entirely, changing which spectral lines can be produced by the remaining electrons in the atom. Cooler stars show strong lines from neutral atoms and even molecules, while hotter stars display lines from ionized species that require more energy to produce through atomic excitation. By examining which lines dominate the spectrum, astronomers can determine the surface temperature of a star without ever visiting it or placing a thermometer on its surface. Beyond identifying elements and measuring temperature, spectroscopy reveals information about pressure and density in stellar atmospheres through subtle details in the shapes of spectral lines themselves. Absorption lines are not infinitely sharp but have a certain width, and this width depends on conditions in the atmosphere where the absorption is occurring during photon transit. Higher pressure causes lines to broaden through collisions between atoms, while lower pressure produces narrower lines, because atoms have more space and fewer interactions with their neighbors. These line widths help astronomers determine the surface gravity of stars, distinguishing compact dwarfs from extended giants, even when their temperatures are similar in measured value from Earth. The motion of a star toward or away from Earth can also be detected through spectroscopy, using the phenomenon known as the Doppler shift in light waves. When a star moves toward us, its light waves are compressed slightly, shifting all spectral lines toward the blue end of the spectrum at shorter wavelengths than expected. When a star moves away, the waves are stretched, shifting lines toward the red end at longer wavelengths, and the amount of shift reveals the velocity precisely. This technique allows astronomers to measure stellar velocities with remarkable precision, detecting motions of just a few meters per second in the most careful observations made with modern instruments. For HD 140283, spectroscopy has been essential in understanding its nature and establishing its credentials as one of the oldest stars accessible to detailed study from Earth. The spectrum of the Methuselah star shows unusually weak absorption lines from iron and other heavy elements, indicating a composition far more primitive than stars like our Sun that formed in enriched environments. This chemical poverty is not a defect, but a timestamp, marking the star as a product of an era when heavy elements were scarce throughout the cosmos. The spectroscopic evidence for low metallicity was among the first clues that HD 283 was genuinely ancient, born in the universe's earliest stellar generation, long before our Sun. When astronomers analyze the spectrum of a star like HD 140283, they are performing a kind of archaeology, reading chemical signatures preserved from the time of formation. The atoms in the stellar atmosphere have remained largely unchanged since the star coalesced from primordial gas, preserving a record of conditions billions of years ago in the early universe. Heavy elements present in the original gas cloud were incorporated into the star, and their spectral lines persist today as evidence of that ancient chemical environment. By measuring the strength of these lines, astronomers can determine precisely how much iron or oxygen or calcium was present when the star formed in the distant past. The process of spectroscopic analysis requires extremely precise measurements, comparing observed line strengths to theoretical predictions based on atomic physics and stellar atmosphere models in great detail. Each absorption line must be carefully identified, matched to a specific atomic transition that produces absorption at that exact wavelength in the electromagnetic spectrum being analyzed. The line depth depends on how many atoms of that element are present in the atmosphere, allowing astronomers to calculate abundances with remarkable precision from distant observations. Modern spectrographs can measure these features with accuracy of better than 1%, revealing subtle differences in composition that would have been invisible to earlier instruments and techniques. The equipment used for spectroscopy has evolved enormously since Fraunhofer's time, progressing from simple prisms to sophisticated diffraction gratings and digital detectors of extraordinary sensitivity today. Early spectrographs used photographic plates to record spectra, requiring long exposures and careful chemical processing before the data could be analyzed by the waiting astronomers afterward. Modern instruments use charge-coupled devices similar to digital camera sensors, converting light directly into electronic signals that can be processed immediately by computers for rapid scientific analysis. These advances have made it possible to obtain high-quality spectra from faint stars like HD 140283, extracting information that would have been inaccessible to astronomers just a few decades ago. The Methuselah star has been observed spectroscopically hundreds of times over the decades, as astronomers have sought to refine their measurements of its chemical composition with ever greater precision. Each new generation of instruments has revealed more detail, allowing more accurate determinations of the abundances of iron, oxygen, and other key elements relevant to age calculations. These improved measurements have been crucial in resolving the age paradox, because small errors in composition translate into significant uncertainties in the calculated age of the star. The patient accumulation of better data over many years has been essential to understanding this ancient object and correcting earlier estimates that seemed to violate cosmic logic. Beyond the chemical composition, spectroscopy reveals the physical conditions in the stellar atmosphere, providing constraints on temperature and surface gravity that feed into evolutionary models of stellar development. The balance of ionized and neutral species in the spectrum indicates how hot the outer layers are, while line widths reveal the pressure and density of the atmosphere. These physical parameters must be determined accurately before meaningful abundance measurements can be made, because the strength of absorption lines depends on conditions as well as composition. For HD 1406-283, careful spectroscopic analysis has established a surface temperature around 5700 Kelvin and a surface gravity consistent with a subgiant star in transition. The information encoded in starlight seems almost miraculous when you consider what we can learn from photons that have traveled for centuries across the void of interstellar space. A beam of light from HD 140283 carries within it the signature of every element in the stellar atmosphere, each leaving its mark at characteristic wavelengths in the spectrum. That same light tells us the temperature and pressure and even the velocity of the star, all from careful analysis of patterns invisible to the naked eye. The universe is remarkably generous with information, encoding its secrets in light. For anyone patient enough to develop the tools to read the cosmic messages arriving constantly, spectroscopy remains the foundation of stellar astrophysics, the technique that transformed astronomy from a science of positions and motions into a true physics of celestial objects in the universe. Every major advance in our understanding of stars has depended on spectroscopic observations, from the discovery of helium in the sun to the measurement of cosmic expansion through galactic redshifts. For ancient stars like the Methuselah star, spectroscopy provides the chemical evidence that establishes their antiquity beyond any reasonable doubt among astronomers studying stellar populations. The nearly pristine composition of HD 140283, with its remarkable deficit of heavy elements, marks it unmistakably as a survivor from the universe's earliest epoch of star formation. As we continue our exploration, the spectroscopic evidence will combine with other measurements to build a complete picture of this remarkable star and its extraordinary history. We will see how the chemical information feeds into stellar evolution models, allowing astronomers to estimate when this ancient sun began its life billions of years ago. And we will understand why small uncertainties in spectroscopic measurements can translate into significant uncertainties in age, contributing to the paradox that initially seemed so troubling to researchers. The light from HD 140283 has been telling its story for centuries, and we have finally developed the tools to understand what it has been saying all along. In the next part, we will explore the Hertzsprung-Russell diagram, the remarkable tool that maps the lives of stars and reveals where each sits in its evolutionary journey. One of the most powerful tools in stellar astronomy is a simple graph, plotting the brightness of stars against their surface temperature on two perpendicular axes. This diagram was developed independently in the early 20th century by two astronomers, Ejnar Hertzsprung in Denmark and Henry Norris Russell in America, working separately on the same fundamental question. They wanted to understand whether stars fell into natural categories, and when they plotted the available data, a striking pattern emerged that would revolutionize stellar astrophysics entirely. The Hertzsprung-Russell diagram, as it came to be called, revealed that stars are not scattered randomly, but cluster into distinct regions reflecting different stages of stellar evolution. The horizontal axis of the diagram represents temperature, but by astronomical convention, it runs backward, with hotter blue stars on the left and cooler red stars on the right side. The vertical axis shows luminosity, the total amount of energy a star radiates per second, with the most brilliant stars at the top and dimmest stars at the bottom. When astronomers plotted hundreds and then thousands of stars on this diagram, they found that most fell along a diagonal band running from the upper left to lower right. This band is called the main sequence, and it represents stars in the prime of their lives, steadily burning hydrogen in their cores as their primary energy source. Our Sun sits on the main sequence, a yellow star of modest temperature and moderate luminosity, positioned roughly in the middle of the band among the stellar population. Hotter blue stars lie above and to the left, burning furiously bright but consuming their fuel rapidly because higher temperatures mean faster nuclear reactions in the stellar core. Cooler red stars lie below and to the right, dimmer and longer-lived, burning their hydrogen slowly over timescales far exceeding the Sun's 10 billion-year expected lifetime. The position of a star on the main sequence depends almost entirely on its mass, with heavier stars burning hotter and brighter than their lighter counterparts in the galaxy. But not all stars fall on the main sequence, and the exceptions reveal the later stages of stellar evolution that await every star after its core hydrogen is exhausted completely. In the upper right corner of the diagram lie the red giants, cool but extremely luminous stars that have expanded enormously as they age beyond the main sequence phase. In the lower left corner are the white dwarfs, hot but very dim because they are tiny remnants of stars that have finished their nuclear burning entirely. These different regions of the diagram represent different chapters in the stellar life. Story and movement between them traces the evolutionary path every star must eventually follow. The Hertzsprung-Russell diagram works as a cosmic clock, because stars spend different amounts of time in each region depending on their mass and evolutionary state at any moment. A star on the main sequence is burning hydrogen steadily, a process that takes billions of years for a star of the Sun's mass to complete fully. When the hydrogen runs out, the star moves off the main sequence relatively quickly, spending a much shorter time as a giant before ending its life as a compact remnant. By determining where a star currently sits on the diagram, astronomers can estimate how far through its life cycle it has progressed, and thus how old it must be. The key to using the HR diagram for age determination lies in understanding the theoretical tracks that stars follow as they evolve through their nuclear burning lifetimes. Astrophysicists have developed sophisticated computer models that simulate the internal structure of stars, tracking how the core composition changes as hydrogen fuses into helium over billions of years. These models predict exactly how a star's temperature and luminosity will change as it ages, tracing a path across the HR diagram that depends on the initial mass. By comparing the observed position of a star with these theoretical tracks, astronomers can determine its current evolutionary state and estimate its age with reasonable precision. For HD 140283, the position on the HR diagram places it just above the main sequence, in the region occupied by subgiant stars beginning their transition toward giant status. This tells us the star has exhausted the hydrogen in its core and begun burning hydrogen in a shell surrounding the inert helium center that has accumulated. The main sequence lifetime for a star of this mass is around 10 billion years, so reaching the subgiant phase indicates the star is at least that old already. But the exact age depends on subtle details of the stellar models, including assumptions about composition and nuclear physics that affect the pace of evolution significantly. The concept of isochrones is essential for precise age determination using the HR diagram, representing lines that connect stars of the same age but different masses together. If you could observe a group of stars that all formed at exactly the same time from the same gas cloud, they would lie along one isochrone today. More massive stars would have evolved further off the main sequence, while less massive stars would still be burning hydrogen steadily on the main sequence band itself. By fitting observed stellar properties to theoretical isochrones, astronomers can estimate the age of individual stars or entire clusters with remarkable precision when the physics is well understood. For ancient stars like the Methuselah star, the isochrone fitting technique must account for the unusual chemical composition because metallicity affects how stars evolve over their lifetimes. Low metallicity stars have different internal structures than metal-rich stars of the same mass, because the scarcity of heavy elements changes how energy flows through the stellar interior. The opacity of stellar material, meaning how easily light passes through it, depends strongly on composition, and opacity affects temperature gradients and evolution rates throughout the star's life. Theoretical isochrones for low metallicity stars differ from those for solar composition stars, and using the wrong models would produce incorrect age estimates for objects like HD 140283. The position of HD 140283 on the HR diagram, combined with its known low metallicity, allowed astronomers to estimate its age by fitting appropriate isochrones to the observations. Early studies using the best available data and models suggested an age around 14.5 billion years. placing the star older than the universe itself seemed to be. This result was clearly impossible, creating the paradox that demanded resolution through improved measurements and refined theoretical understanding of how ancient stars evolve over cosmic timescales. The HR diagram had revealed something was wrong somewhere, either in the observations or in the physics underlying the theoretical models used for age calculation purposes. The power of the HR diagram lies in its ability to organize the diversity of stars into a coherent framework that reveals underlying physical principles governing stellar behavior. A century after its creation, this simple graph remains the fundamental tool for understanding stellar populations, as essential today as when Hertzsprung and Russell first drew their plots. Every introductory astronomy course teaches the HR diagram, and every research paper on stellar evolution references it, because no other single tool provides such clear insight into stellar lives. For the Methuselah star, the diagram placed crucial constraints on possible ages, narrowing the range and highlighting the tension with accepted cosmic chronology measurements of universal age. The movement of a star across the HR diagram is imperceptibly slow by human standards, taking millions or billions of years to show significant change in position. We cannot watch a star evolve in real time because even the fastest evolutionary phases take longer than human civilization has existed in recorded history on Earth. Instead, we observe many different stars at different stages, like viewing snapshots of many different people to understand the human aging process without watching anyone grow old. The HR diagram assembles these snapshots into a coherent narrative, allowing us to reconstruct the stellar life cycle from birth to death across cosmic time spans. HD 140283 represents a snapshot of an ancient star caught in the act of transitioning from main sequence hydrogen burning to the giant phase of its existence. This transition phase is relatively brief in cosmic terms, lasting only a few 100 million years, a small fraction of the star's total lifetime since formation. The fact that we observe the Methuselah star in this phase is somewhat lucky, because most of its existence was spent on the main sequence, where it looked different. In another billion years, it will have expanded into a full red giant, then shed its outer layers to become a white dwarf, slowly cooling forever. The HR diagram teaches us that stars are not eternal, unchanging points of light, but dynamic objects undergoing slow transformation across billions of years of continuous nuclear burning. The Methuselah star has already lived through most of its active life, and its remaining years as a nuclear-powered object are numbered in the billions still ahead. But even those billions will eventually end as the star exhausts all available fuel and settles into the quiet retirement of a white dwarf remnant phase. The diagram maps this entire journey, from birth on the main sequence to death as a cooling cinder, revealing the destiny that awaits every star in the galaxy. Understanding the HR diagram is essential for appreciating how astronomers calculated the age of HD 140283 and why the initial result seemed so deeply troubling to the community. The diagram placed the star in a specific evolutionary phase, and models of that phase predicted how long it takes to reach from the beginning of hydrogen burning. When those predictions exceeded the age of the universe, something had to be wrong, either in the observations or the theoretical framework underlying the age calculations. Resolving that tension would require years of careful work, improving measurements, and refining models until the numbers finally began to agree with cosmic logic. In the next part, we will explore the concept of stellar generations, understanding why the earliest stars had such different chemical compositions than stars born later in cosmic history. The stars we see in the night sky are not all alike, and their differences extend far beyond the obvious variations in brightness and color visible to our eyes. Some stars are young by cosmic standards, born just millions of years ago, from gas clouds enriched with heavy elements produced by countless earlier stellar generations before them. Others are ancient, formed in the early universe when the cosmos was young and heavy elements were scarce throughout the primordial material available for star formation. Astronomers have classified stars into distinct populations based on their ages and chemical compositions, revealing a cosmic genealogy that traces back to the universe's earliest epochs. The concept of stellar populations was introduced by German astronomer Walter Baade during the 1940s, based on his careful observations of stars in the Andromeda galaxy and elsewhere. Baade noticed that stars in different regions of galaxies had systematically different properties, with those in spiral arms appearing younger and bluer than stars in central bulges and halos. He proposed dividing stars into two populations, imaginatively named Population I and Population II, based on their locations and apparent characteristics within galactic structures observed from Earth. This classification scheme has proven remarkably useful for understanding stellar evolution and the big, chemical history of galaxies across billions of years of cosmic time, since the Big Bang. Population Y stars are the young, metal-rich stars found primarily in the thin disk of spiral galaxies, orbiting the galactic center in orderly circular paths alongside their neighbors. Our Sun is a typical Population I star, formed about 4.6 billion years ago from gas that had been enriched by many previous stellar generations of nucleosynthesis. These stars contain significant amounts of iron, oxygen, carbon, and other heavy elements, incorporated from the interstellar medium at the time of their formation in molecular clouds. The presence of these heavy elements affects their internal structure and evolution, making Population I stars somewhat different from their more ancient counterparts in the galactic halo. Population II stars are older and metal-poor, found primarily in the galactic halo and central bulge following chaotic orbits that take them far from the orderly disk structure. These stars formed early in the galaxy's history, before supernova explosions had enriched the interstellar medium with significant amounts of heavy elements beyond the primordial hydrogen and helium. Their low metallicity is a timestamp, marking them as products of an era when the cosmos was chemically primitive compared to the enriched environment that produced our Sun. HD 140283 is a classic Population II star, its composition and orbit identifying it as a survivor from the galaxy's ancient past when conditions were very different. The difference between Population I and Population II reflects the gradual chemical enrichment of the universe over billions of years of stellar evolution and supernova recycling of matter. When the universe began, only hydrogen and helium and traces of lithium existed, created during the first few minutes of the Big Bang through primordial nucleosynthesis processes. Heavier elements simply did not exist because the temperatures and densities required to forge them could only be found in the cores of stars that had not yet formed. The first generation of stars had to form from this pristine material, containing essentially no metals by the astronomical definition of elements heavier than helium. Astronomers have hypothesized a third category, called Population 3, representing the very first stars that formed from purely primordial gas in the early universe, before any enrichment. These hypothetical first stars have never been directly observed, and they may have all died long ago because theoretical models suggest they were extremely massive and short-lived. Massive stars burn through their nuclear fuel rapidly and explode as supernovae within just a few million years, far too briefly to survive to the present day. The death of Population 3 stars would have enriched the primordial gas with the first heavy elements, enabling the formation of Population 2 stars afterward in the next generation. The search for true Population 3 stars continues because finding even one would provide invaluable information about conditions in the very early universe before chemical enrichment began. Some astronomers have looked for extremely metal-poor stars that might be surviving Population 3 objects, but none have been confirmed as completely free of heavy elements to date. The most metal-poor stars known, including HD 140283, still contain trace amounts of iron and other metals, indicating they formed after at least some enrichment had already occurred. These stars are sometimes called Population 2.5, extremely ancient but not quite primordial, born in the transition period when the first heavy elements were becoming available. HD 140283 belongs to this ancient population, formed in the first billion years after the Big Bang, when heavy elements were scarce but not entirely absent from the cosmos. Its extremely low metallicity places it among the most chemically primitive stars known, suggesting formation very early in the process of galactic chemical evolution and enrichment over time. The presence of even small amounts of iron and other metals indicates that some earlier stars had already lived and died before HD 140283 formed from their enriched debris. This star is therefore not truly primordial, but it formed close enough to the beginning that it preserves chemical signatures from the universe's earliest epochs of star formation. The galactic halo, where HD 140283 originated, is a spherical distribution of old stars and globular clusters surrounding the Milky Way's flattened disk like a ghostly envelope. This halo contains some of the oldest objects in our galaxy, relics from an era before the disk had formed from the collapsing primordial gas cloud. Halo stars follow elongated orbits that take them far above and below the galactic plane, carrying them through neighborhoods very different from their birthplaces long ago. HD 140283 is currently passing through the solar neighborhood. On such an orbit, a temporary visitor from the ancient halo that will eventually return to more distant regions. The concept of stellar generations helps explain why some stars have such different compositions than others. Tracing the flow of matter through cosmic time across billions of years, each generation of stars processes hydrogen and helium into heavier elements through nuclear fusion. Then some fraction dies in explosions that scatter those elements into space. The next generation forms from gas enriched by these deaths, incorporating the heavy elements produced by earlier stars into their structure from the moment of formation onward. This cosmic recycling has been ongoing for over 13 billion years, gradually building up the heavy element content of the universe, generation by generation, throughout cosmic history. Population 2 stars like HD 140283 formed early in this recycling process, when only a few generations of massive stars had lived and died to enrich the available gas. Their low metallicity reflects this early timing, a chemical timestamp that cannot be altered by subsequent evolution of the star itself once formation is complete. The heavy elements present in the stellar atmosphere were incorporated at birth and have remained largely unchanged for over 12 billion years of steady burning since then. By measuring these ancient compositions, astronomers can learn about conditions in the early universe that would otherwise be inaccessible to direct observation from our current cosmic vantage point. The difference in metallicity between population I and population 2 stars is substantial, amounting to factors of 100 or more in the abundance of elements like iron relative to hydrogen. Our Sun contains about 1 iron atom for every 30,000 hydrogen atoms, a ratio that reflects billions of years of stellar nucleosynthesis and enrichment before its formation. HD 140283 contains roughly 1 iron atom for every 6 million hydrogen atoms, about 200 times less iron than the Sun, marking its ancient and primitive origins. This dramatic difference in chemical composition is the key evidence for the star's extreme age, confirming that it formed in a very different era of cosmic history. Understanding stellar generations helps place HD 140283 in context, revealing why astronomers were so confident it was genuinely ancient even before detailed age calculations were attempted. Everything about this star pointed to extreme antiquity, its halo orbit and high velocity and remarkably low metallicity, all consistent with formation in the early universe. The age paradox arose not because anyone doubted the star was old, but because the calculated age seemed to exceed what was cosmically possible given other measurements. Resolving that paradox would require deeper understanding of how chemical composition affects age determination, a topic we will explore in more detail in the next part of our journey. The flow of matter through stellar generations connects us to the ancient universe in ways that are both scientifically profound and strangely personal when we stop to contemplate them. The iron in our blood and the calcium in our bones were forged in stars that lived and died billions of years before our Sun and solar system existed. We are literally made of stellar material, recycled through multiple generations of cosmic chemistry before finding its way into living forms on this small rocky planet. HD 140283 represents an earlier chapter in this cosmic story, a star born before the elements we are made of had even been created in significant abundance. Now we will examine the chemistry of cosmic dawn more closely, understanding how astronomers use spectroscopic signatures to determine the age of ancient stars like Methuselah. The chemical composition of a star serves as a cosmic timestamp, encoding information about the conditions that prevailed when the star formed from collapsing interstellar gas billions of years ago. For ancient stars like HD 140283, this chemical signature is remarkably primitive, revealing a universe that had not yet been enriched by many generations of stellar nucleosynthesis. By measuring the abundances of various elements in the stellar atmosphere, astronomers can determine when a star most likely formed relative to the beginning of cosmic time. The Methuselah star's extreme chemical poverty is the primary evidence for its astonishing age, marking it as a survivor from the universe's earliest stellar epoch of formation. When the universe emerged from the Big Bang approximately 13.8 billion years ago, only the lightest elements existed in the hot, dense primordial plasma of early creation. During the first few minutes, nuclear reactions fused protons and neutrons into helium nuclei, along with trace amounts of lithium and deuterium as minor products. But the universe was expanding and cooling rapidly, and within about 20 minutes, the conditions for nuclear fusion had passed, freezing in a composition of roughly 75% hydrogen and 25% helium by mass throughout the cosmos. This primordial composition contained no carbon, no oxygen, no iron, and no other elements heavier than lithium in any significant amount anywhere in the young universe. The entire periodic table beyond lithium simply did not exist, because those elements require stellar cores to forge them through nuclear fusion at temperatures and densities unavailable in the expanding early universe. The first generation of stars had to form from this chemically barren material, and they were probably very different from the stars we see today in the enriched galaxy. Without heavy elements to help gas clouds cool and collapse, the first stars may have been extremely massive, hundreds of times the sun's mass, burning furiously bright. But briefly, those first massive stars lived fast and died young, exploding as supernovae within just a few million years of their formation and scattering freshly synthesized heavy elements into the surrounding gas. In their cores, nuclear fusion had built helium into carbon, carbon into oxygen, and progressively heavier elements up to iron and beyond, through various processes of stellar nucleosynthesis. The supernova explosions themselves created elements heavier than iron through rapid neutron capture, forging gold and platinum and uranium in the violent final moments of stellar death. This first wave of element creation began the slow enrichment of the universe that would continue for billions of years through countless stellar generations, living and dying afterward. The earliest population 2 stars, including HD 140283, formed from gas that had been lightly enriched by these first supernovae, incorporating trace amounts of heavy elements for the first time. Their metallicity is extremely low but not zero, indicating formation after at least a few cycles of stellar birth and death had begun the enrichment process in their region. The precise abundance pattern of different elements provides clues about what kinds of stars produce the heavy elements that HD 140283 incorporated at its formation billions of years ago. By studying these patterns, astronomers can reconstruct conditions in the early universe when the first stellar generations were living and dying and seeding the cosmos with new elements. The element iron plays a special role in stellar astronomy, serving as the standard reference for measuring the overall metallicity of stars across different populations and ages. Iron is produced primarily in Type Ia supernovae, the explosions of white dwarf stars that accumulate matter from companions, creating a specific nucleosynthetic signature in enriched gas. The ratio of iron to hydrogen in a star's atmosphere, denoted by the symbol Phi/H, is the conventional measure of metallicity used by astronomers worldwide. For HD 140283, This ratio is approximately -2.4 on a logarithmic scale, meaning the star has about 200 times less iron than our Sun possesses. But iron is not the only element of interest for understanding ancient stellar. Chemistry and other elements provide additional clues about the enrichment history of the primordial gas. The alpha elements, including oxygen, magnesium, silicon, and calcium, are produced primarily in the cores of massive stars and released in Type II supernovae from collapsing cores of dead giants. These elements formed first, before Type Ia supernovae became common, because the massive stars that produce them live and die quickly within just a few million years. The relative abundances of alpha elements compared to iron reveal the timescale of chemical enrichment, helping astronomers constrain when HD 140283 formed relative to the first supernova events. HD 140283 shows an enhancement of alpha elements relative to iron, exactly what astronomers expect for a star formed in the early universe before Type I supernovae had contributed significantly. This alpha enhancement is a characteristic signature of population II stars, confirming formation in an era when massive star supernovae dominated the chemical enrichment of the interstellar medium. The specific abundance ratios observed in the Methuselah star match predictions for gas enriched by just a few early supernovae, consistent with formation in the first billion years after the Big Bang. Every chemical measurement points to the same conclusion: 283 is genuinely one of the oldest stars accessible to detailed study from our current vantage point. The element oxygen deserves special attention because its abundance has proven crucial for accurate age determination of ancient stars like the Methuselah star in particular. Oxygen is the most abundant heavy element in the universe, and its presence affects the internal structure of stars in ways that influence evolutionary timescales and calculated ages. The opacity of stellar material, meaning how easily light can escape from the interior, depends significantly on the oxygen abundance present in the stellar plasma. Higher oxygen abundance increases opacity, slowing the rate at which energy escapes and affecting how quickly the star evolves through its nuclear burning phases over billions of years. For many years, the oxygen abundance in HD 140283 was uncertain, with different measurement techniques giving somewhat different results that affected age calculations significantly in either direction. This uncertainty was one of the factors contributing to the apparently impossible age of 14.5 billion years, because inaccurate oxygen abundance led to incorrect evolutionary models. As measurements improved and better understanding of systematic errors developed, the oxygen abundance became better constrained, allowing more accurate age estimates that helped resolve the paradox. The story of the Methuselah star paradox is partly a story about the difficulty of measuring oxygen in ancient stellar atmospheres with sufficient precision for reliable age determination. The spectroscopic archaeology of ancient stars requires extraordinary precision, because small measurement errors can translate into large uncertainties in derived ages and other properties of scientific interest. Absorption lines from oxygen and other elements must be measured against the continuous stellar background with accuracy of better than 1% to yield reliable abundance determinations. Systematic errors from imperfect models of stellar atmospheres can bias results in ways that took years to identify and correct in the literature of astronomical research. The scientific community has worked collaboratively for decades to improve these measurements, gradually converging on more reliable values that better reflect the true composition of stars like HD 140283. The chemical information preserved in HD 140283 represents a direct window into conditions that prevailed more than 12 billion years ago in the early universe, before most cosmic structure existed. The atoms in this star's atmosphere have remained largely unchanged since its formation, preserving a record of primordial chemistry inaccessible through any other means of observation from Earth. By studying stars like this, astronomers can test theories of Big Bang, nucleosynthesis, and early stellar evolution, comparing predictions to preserved evidence from that distant era. The Methuselah star is not just an old object, but a scientific time capsule, carrying information across the ages to anyone patient enough to decode its spectral message. The patience required for this work extends across human generations as well, as cosmic timescales, with each generation of astronomers refining measurements made by their predecessors decades earlier. The first spectroscopic studies of HD 140283 date back to the mid-20th century, when astronomers recognized its unusual composition and began systematic observations with available instruments. Each subsequent generation has applied improved techniques and better theoretical understanding to the same fundamental questions about this star's age and origins in the early universe. The resolution of the age paradox came through this multi-generational effort, accumulating small improvements until the picture finally came into clear focus after many decades. As we continue our exploration, we will examine how astronomers determined the age of the universe itself, establishing the cosmic timeline against which stellar ages must be measured. Understanding how we know the universe is 13.8 billion years old will help explain why an apparently older star created such a paradox, demanding resolution. The story involves cosmic expansion and relic radiation, and the patient work of cosmologists piecing together the history of everything that exists throughout the observable universe. In the next part, we will explore the measurement of cosmic age, understanding how astronomers determined when the universe began its expansion from the initial singularity of the Big Bang. Determining the age of the universe stands as one of the great achievements of 20th century science, a triumph of observation and theory working together across multiple decades. The answer of approximately 13.8 billion years rests on multiple independent lines of evidence, each confirming the others and building confidence in this remarkable measurement of cosmic chronology. Understanding how we arrived at this number helps explain why the Methuselah star paradox was so troubling, because it seemed to contradict our most reliable measurements of cosmic time. If HD 140283 was truly older than the universe, something fundamental about our understanding of cosmology or stellar physics had to be seriously wrong somewhere. The story of cosmic age measurement begins with Edwin Hubble's observations in the 1920s, when he demonstrated that distant galaxies are moving away from us at speeds proportional to their distance. This relationship, now called Hubble's law, implied that the universe is expanding, with the space between galaxies stretching continuously over cosmic time throughout the observable universe. Running this expansion backward in time led to a profound conclusion that everything was once concentrated in a single point of incredible density and temperature long ago. The moment of this initial concentration, when expansion began, marked the birth of the universe and the starting point of all cosmic time that has followed since. The rate of expansion, quantified by the Hubble constant, determines how long ago this beginning occurred by measuring the current pace of cosmic stretching. If the universe is expanding rapidly, it took less time to reach its current size, and the universe is correspondingly younger than if expansion were slow. Measuring the Hubble constant accurately has been a major focus of observational cosmology for decades, because small errors in this value translate directly into large uncertainties in cosmic age. Early estimates of the Hubble constant were quite uncertain, leading to age estimates that varied considerably and sometimes conflicted with geological evidence for Earth's age in embarrassing ways. The original measurements suggested the universe might be only 2 billion years old, which was obviously wrong because Earth's rocks had been dated to over 4 billion years already. A star cannot be older than the universe, and likewise a planet cannot be older than the cosmos that contains it, creating an obvious logical problem for early cosmology. This early age crisis was eventually resolved through improved distance measurements to galaxies, which showed that earlier estimates had significantly underestimated cosmic distances and thus overestimated the expansion rate. The revised Hubble constant implied a much older universe, eventually converging toward the modern value of around 14 billion years of cosmic age since the Big Bang occurred. A completely independent method for measuring cosmic age emerged from the discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson at Bell Labs. This faint glow of microwave radiation fills all of space uniformly, representing the cooled remnant of the hot plasma that filled the early universe before atoms formed. When the universe was about 380,000 years old, it cooled enough for electrons to combine with protons, making neutral atoms for the first time. This transition made the universe transparent, releasing the light that we now observe as the cosmic microwave background stretched to microwave wavelengths by 13 billion years of cosmic expansion. The properties of the cosmic microwave background encode information about conditions in the early universe, including the age and composition of the cosmos at that time when photons began streaming freely. Tiny temperature fluctuations in the background, just 1 part in 100,000, reflect density variations that would eventually grow into the galaxies and clusters we observe today. The pattern of these fluctuations depends on cosmological parameters, including the age, density, and expansion history of the universe, all encoded in the microwave signal from the early cosmos. Satellite missions have mapped the cosmic microwave background with extraordinary precision, extracting these cosmological parameters to multiple decimal places of accuracy through careful analysis. The COBE satellite, launched in 1989, made the first detection of the primordial fluctuations, confirming the basic picture of cosmic evolution from a hot, dense, early state. The WMAP mission, launched in 2001, refined these measurements considerably, providing the first precise determination of cosmic age at 13.7 billion years, with uncertainty of only 200 million years in either direction. The Planck satellite, launched by the European Space Agency in 2009, achieved even greater precision, refining the cosmic age to 13.8 billion years, with uncertainty below 1%. This measurement rests on detailed modeling of how sound waves propagated through the primordial plasma, leaving characteristic patterns in the temperature fluctuations of the microwave background. The agreement between predictions and observations is remarkable, confirming that our understanding of the early universe is fundamentally correct down to fine details of the cosmological model. The cosmic age, derived from Planck data, represents one of the most precise measurements in all of science, anchoring our understanding of cosmic chronology with exceptional reliability. Additional confirmation comes from observations of distant Type Ia supernovae, which serve as standard candles for measuring cosmic distances and the expansion history over billions of years. These supernovae occur when white dwarf stars accumulate enough matter to trigger thermonuclear explosions of remarkably uniform brightness, providing distance indicators visible across cosmic scales. By measuring supernova distances and comparing them to redshifts, astronomers can trace how the expansion rate has changed over time, constraining cosmic age through a completely independent method. The supernova results agree with the microwave background measurements, providing confidence that both are revealing the true history of cosmic expansion since the Big Bang. The convergence of multiple independent measurements on the same cosmic age is deeply reassuring, suggesting that our understanding of the universe is fundamentally correct in its broad outlines. When different techniques based on different physics all yield the same answer, the agreement is unlikely to be coincidental, building confidence in the result obtained through careful observation. The universe is approximately 13.8 billion years old, with uncertainty of less than 1%. One of the most precisely known quantities in all of cosmology today. This precise cosmic age creates the paradox when confronted with a star that appears to be 14.5 billion years old, exceeding the universal limit by several hundred million years. 283 truly had this age. It would have formed before the Big Bang, an obvious impossibility that demands explanation through careful scientific analysis of the measurements. Either the stellar age was wrong, or the cosmic age was wrong, or both contained errors that made them temporarily incompatible until better measurements could be obtained. The astronomical community took this paradox seriously, precisely because both measurements seemed robust individually, each supported by careful work and multiple independent confirmations of the results. The cosmic age from the microwave background was not easily dismissed, resting on detailed physics and precise satellite observations of primordial radiation filling all of space. The stellar age from isochrone fitting was also carefully derived, based on well-understood stellar physics and spectroscopic measurements of the Methuselah star's properties in multiple studies. Finding the resolution required examining both sets of assumptions carefully, looking for sources of error that might have been overlooked in either measurement or the underlying theoretical framework. The tension between stellar and cosmic ages was not unique to HD 140-283, having appeared before in other contexts as astronomers refined their techniques over the decades. Globular clusters, ancient spherical collections of stars found in galactic halos, had also sometimes yielded ages that seemed uncomfortably close to or exceeding the cosmic age limit. These tensions had historically been productive, driving improvements in both stellar evolution, theory, and cosmological measurements until agreement was eventually achieved through patient scientific work. The Methuselah paradox was the latest installment in this ongoing dialogue between stellar astronomy and cosmology, each field refining the other through productive tension across decades. The resolution would come not from any dramatic new discovery, but from the patient accumulation of improved measurements and refined theoretical models over many years of careful work. Better distance determinations and updated chemical abundances and improved nuclear physics would all contribute to bringing the stellar age down into agreement with cosmic chronology. The scientific process worked exactly as it should, taking an apparent contradiction seriously and working through every possible source of error until resolution emerged through collaborative effort. In the next part, we will examine the initial collision between these measurements in more detail, understanding exactly how the numbers conflicted and what astronomers tried first to resolve the paradox. The publication of an age estimate exceeding 14 billion years for HD 140283 created genuine concern in the astronomical community, because the implications seemed to challenge fundamental cosmology, if correct. The star appeared to be approximately 700 million years older than the universe itself, a logical impossibility that demanded either new physics or recognition of serious measurement errors. Astronomers understood that one or both numbers had to be wrong, but identifying exactly where the error lay required careful examination of every assumption underlying both calculations. The scientific process of resolving this paradox would take years, illustrating both the power and the patience of collaborative scientific inquiry when confronting genuine puzzles. The age estimate for HD 140283 came from fitting the star's observed properties to theoretical isochrones, the lines of constant age on the Hertzsprung-Russell diagram that trace stellar evolution. The star's position on this diagram, combined with its measured chemical composition, allowed astronomers to estimate when it most likely formed by finding the matching isochrone for its properties. This technique is well established and has been applied successfully to many stars and stellar clusters, generally producing ages consistent with other constraints on cosmic chronology. But the method depends on several inputs, each of which carries measurement uncertainty that propagates through to the final derived age in ways that can be significant. The critical inputs for age determination include the star's luminosity, temperature, and chemical composition, each of which must be measured with high precision for reliable results. Luminosity depends on both apparent brightness, which is easily measured, and distance, which is much harder to determine accurately for stars outside our immediate neighborhood in the galaxy. Temperature comes from spectroscopic analysis, comparing observed line strengths to theoretical models of stellar atmospheres, a process that requires accurate atomic physics data and careful treatment of systematic errors. Chemical composition, particularly the abundances of helium and oxygen, affects how stars evolve and must be measured precisely for accurate isochrone fitting to observational data. The distance to HD 140283 was initially determined using the parallax method, measuring the tiny apparent shift in position as Earth orbits the Sun each year around the solar center. This shift is extremely small for a star 200 light-years away, amounting to only about 23 milliarc seconds, a challenging measurement even with good telescopes and careful technique. Ground-based parallax measurements were limited by atmospheric distortion, introducing uncertainty that propagated through to luminosity and ultimately to the derived age of the star. An error of just a few percent in distance could change the calculated age by hundreds of millions of years, enough to potentially resolve or exacerbate paradoxes in the data. The chemical composition of HD 140283 also carried measurement uncertainty, particularly for elements like oxygen that strongly influence stellar evolution models and derived ages in isochrone calculations. Different observational techniques yielded somewhat different oxygen abundances, and resolving these discrepancies required understanding subtle systematic effects in spectroscopic analysis that took years to fully characterize. The helium abundance was even harder to measure, because helium lines are very weak in stars of this temperature and require special techniques to observe reliably in spectra. These composition uncertainties fed into the age calculation in complex ways, interacting with distance uncertainties to produce the disturbingly high estimate that seemed to violate cosmic chronology. The theoretical models used for age determination also contained assumptions that might be incorrect, particularly regarding the physics of very old metal-poor stars like HD 140283. Stellar evolution models require inputs about nuclear reaction rates, energy transport mechanisms, and the equation of state for stellar material, each carrying uncertainty from laboratory measurements. For ancient metal-poor stars, the models had been less thoroughly tested than for solar composition stars, leaving open the possibility of systematic errors affecting age calculations. Perhaps the physics of hydrogen burning in extremely metal-poor cores differed slightly from what models assumed, shifting ages by enough to resolve the paradox with improved theoretical treatment. The astronomical community responded to the paradox with a multi-pronged approach, seeking to improve every measurement and model that contributed to the age calculation for this puzzling star. Observers planned new parallax measurements using space-based telescopes free from atmospheric distortion, promising much higher precision in the crucial distance determination needed for accurate luminosity. Spectroscopists designed new observations to better constrain oxygen and other abundances, using multiple independent techniques to check for systematic errors that might bias results. Theorists re-examined stellar evolution codes, updating nuclear physics inputs and testing alternative treatments of convection and opacity that might affect calculated ages for metal-poor stars. The process of resolving scientific paradoxes rarely involves a single dramatic breakthrough, but rather the slow accumulation of small improvements that gradually bring clarity to confusing situations. Each improved measurement narrowed the uncertainty slightly, while each refined model reduced systematic errors that had biased earlier results in ways not previously recognized by researchers. The Methuselah paradox would be resolved through exactly this kind of patient, incremental progress, as astronomers spent years refining their understanding of this ancient star's properties. The scientific community worked collaboratively, with different groups contributing complementary expertise and checking each other's work to ensure reliability of the slowly converging results. The importance of error bars became central to discussions of the paradox, as astronomers recognized that quoted uncertainties might not fully capture all sources of possible error. A measurement of 14.5 billion years with an uncertainty of plus or minus 1 billion years could potentially be consistent with a cosmic age of 13.8 if the uncertainties were properly characterized throughout. But the early uncertainties seemed too small to bridge the gap, suggesting that either the measurements were more precise than they had right to be, claimed as. Understanding and properly quantifying all sources of uncertainty became crucial for determining whether the paradox was real or merely apparent and resolvable through better error analysis. The tension between stellar and cosmic ages was uncomfortable but scientifically productive, forcing improvements in both fields that would benefit future research beyond this specific paradox itself. Cosmologists re-examined their age determination to ensure no systematic errors lurked in. The microwave background analysis, confirming the robustness of the 13.8 billion year result. Stellar astronomers scrutinized every aspect of isochrone fitting, identifying sources of uncertainty that had been underestimated and developing better techniques for future age determinations of ancient stars. The paradox served as a catalyst for methodological improvements that strengthened the foundations of both fields. Through careful, collaborative work over many years of investigation, some scientists considered more exotic possibilities that would preserve both measurements by altering our understanding of fundamental physics in ways that might allow impossible ages. Perhaps the universe had undergone episodes of different expansion rates that complicated the simple age calculation from current observations of cosmic expansion and the microwave background radiation. Or perhaps stellar evolution at very low metallicity differed from expectations in ways that made isochrone dating unreliable for the most ancient stars in the galactic halo. These exotic possibilities were considered seriously, but ultimately proved unnecessary, as improved conventional measurements gradually brought the numbers into agreement without requiring new physics. The resolution of the paradox would vindicate the scientific process, demonstrating that careful attention to sources of error can resolve apparent contradictions without overturning established understanding. The universe remained 13.8 billion years old, and the Methuselah star's age was revised downward to a value compatible with this cosmic age limit. The process took years of careful work by many researchers, each contributing pieces to a puzzle that eventually assembled into a coherent picture of cosmic chronology. The patience required for this resolution exemplifies how science actually works, in practice, through slow, steady progress rather than dramatic, revolutionary breakthroughs in most cases. The key improvements came in two areas: distance determination and chemical abundance measurement, both of which significantly affected the derived age when updated values were incorporated. Better distances from space-based observations revised the star's luminosity, while improved oxygen abundances changed how stellar evolution models predicted its age based on current properties. These improvements, combined with refined theoretical treatment of metal-poor stellar evolution, finally brought HD 140-283 into the cosmic family as a legitimately ancient but not impossibly old object. In the next part, we will examine the distance improvements in detail, understanding how space-based observations refined our knowledge of the Methuselah star's position in the cosmic neighborhood. The distance to a star is one of the most fundamental yet challenging measurements in all of astronomy, underlying nearly every other property we seek to determine about distant objects. For HD 140-283, accurate distance measurement proved crucial for resolving the age paradox, because even small errors in distance translate into significant changes in calculated luminosity and derived age. The story of how astronomers refined this measurement illustrates both the challenges of precision astronomy and the power of space-based observations to overcome limitations of Earth-bound telescopes. The Methuselah star's distance, ultimately measured with unprecedented precision, was key to bringing its age into agreement with the cosmic timeline established by independent measurements. The fundamental technique for measuring stellar distances is parallax, exploiting the slight shift in apparent position that occurs as Earth orbits the Sun each year around its path. Imagine holding your thumb at arm's length and alternating which eye is open, watching how your thumb seems to shift against the background of more distant objects. This shift occurs because your two eyes view the thumb from slightly different positions, and the amount of shift depends on how far away the thumb is held. Stars show the same effect, appearing to shift slightly against more distant background stars as Earth moves from one side of its orbit to the other every 6 months. For nearby stars, this parallax shift is measurable but extremely small, typically less than 1 arcsecond even for the closest stars beyond our solar system entirely. An arcsecond is 1/3600th of a degree, roughly the apparent size of a coin viewed from several kilometers away, an incredibly tiny angle to measure accurately. The nearest star system, Alpha Centauri, shows a parallax of about 3/4 of an arcsecond, while HD 140283 at 200 light-years shows only 23 milliarcseconds of apparent motion. Measuring such tiny angles requires extremely precise instruments and careful attention to every source of error that might bias the result in one direction or another. Ground-based parallax measurements face a fundamental limitation from Earth's atmosphere, which causes stars to twinkle and blurs their positions in ways that limit precision of measurements. Atmospheric turbulence shifts stellar images around randomly, introducing noise that obscures the tiny systematic shift caused by Earth's orbital motion around the Sun each year. Even under excellent conditions at the best observatory sites, ground-based parallaxes rarely achieve precision better than a few milliarcseconds, limiting distance accuracy to roughly 10% for stars at HD 140283's distance away. The Hipparcos satellite, launched by the European Space Agency in 1987, revolutionized parallax measurement by observing from above the atmosphere in Earth orbit for several years. Free from atmospheric distortion, Hipparcos measured positions with precision of about 1 milliarsecond, a dramatic improvement over ground-based capabilities that enabled much better distance determinations for nearby stars. The satellite's catalogue included a parallax measurement for HD 140283, providing an improved distance estimate that was significantly more reliable than earlier ground-based values had been. But even Hipparcos precision left room for uncertainty at the level needed for extremely precise age calculations that might resolve or confirm the paradox surrounding this ancient star. The breakthrough came from observations with the Hubble Space Telescope, using a specialized mode designed for precision astrometry of individual stars rather than imaging extended astronomical objects. Hubble's fine guidance sensors can measure stellar positions with accuracy of about half a milliarsecond, several times better than Hipparcos achieved in its comprehensive survey of bright stars. A team of astronomers, led by Howard Bond, dedicated substantial Hubble observing time to HD 1406-283, measuring its parallax over multiple years to reduce random errors through repeated observation. The investment of precious telescope time reflected the scientific importance of resolving the age paradox for this remarkable ancient star in the galactic halo. The Hubble observations yielded a parallax of 17.15 milliarseconds, with an uncertainty of only 0.14 milliarseconds, an extraordinary precision of less than 1%. This translated to a distance of 190.1 light-years, with uncertainty of only about 1.5 light-years, pinning down the star's location with unprecedented accuracy. The improved distance was slightly different from earlier estimates, and this difference propagated through to revised luminosity and ultimately to a reduced age estimate for the Methuselah star. Better distance meant better luminosity, and better luminosity meant better isochrone fitting, each improvement contributing to resolution of the paradox that had troubled astronomers for years. The connection between distance and age might seem indirect, but it becomes clear when we trace how each measurement feeds into the age calculation step by step. Luminosity, the intrinsic brightness of a star, depends on both the apparent brightness we observe and the distance light must travel before reaching our telescopes on Earth. If we underestimate the distance, we underestimate the luminosity, because a nearby star would not need to be as intrinsically bright to appear equally luminous as a more distant star would. Conversely, overestimating distance makes the star seem more luminous than it truly is, shifting its position on the HR diagram and affecting age calculations. For HD 140283, the revised Hubble distance placed the star at a slightly different luminosity than earlier estimates had suggested, affecting where it appeared on the evolutionary tracks of stellar models. This shift, combined with other improvements in chemical abundance measurements, contributed to bringing the age estimate down from the impossible 14.5 billion years. The new distance alone did not solve the paradox entirely, but it was a crucial piece of the puzzle that helped resolve the age crisis when combined with other refinements. Precision astrometry from space proved essential for making progress on this decades-old problem that had resisted solution with ground-based measurements alone due to atmospheric limitations. The Gaia satellite, launched by the European Space Agency in 2013, has since provided even more precise parallax measurements for millions of stars throughout the galaxy. Gaia's precision exceeds even Hubble's for many targets, measuring parallaxes with uncertainty of just tens of micro-arc-seconds for bright nearby stars, representing another leap forward in precision astrometry. The Gaia parallax for HD 140283 confirms and refines the Hubble measurement, providing independent verification that the distance is now known with extraordinary accuracy for this ancient star. This convergence of multiple measurement techniques gives astronomers confidence that distance-related errors are no longer a significant source of uncertainty in age calculations for the Methuselah star. The era of parallax uncertainty contributing substantially to the age paradox has effectively ended thanks to these remarkable space-based missions orbiting far above Earth's atmosphere. The story of parallax measurement spans centuries, from the first attempts by ancient Greek astronomers to modern spacecraft achieving micro-arc-second precision in their observations of stellar positions. Early astronomers tried to detect stellar parallax as evidence that Earth orbits the north, but their instruments lacked the precision needed to measure such tiny angular shifts. Friedrich Bessel made the first successful parallax measurement in 1838, determining the distance to the star 61 Cygni and confirming the heliocentric model beyond any remaining doubt. Nearly 2 centuries later, we can measure the same effect with precision, millions of times better, opening windows into stellar physics that Bessel could never have imagined possible. For the Methuselah star specifically, the journey from uncertain ground-based parallax to precise space-based measurement took decades of patient work and technological advancement in instrumentation. Each improvement in distance accuracy propagated through to better constraints on luminosity, and therefore on the star's position along its evolutionary track on the HR diagram. The cumulative effect of these refinements was substantial, contributing meaningfully to reducing the estimated age from impossible values towards numbers compatible with the known age of the universe. Distance measurement may seem like a technical detail, but for HD 140283, it proved to be one of the critical factors in resolving a fundamental paradox about cosmic time. The importance of precise distance extends beyond just this one star, because parallax provides the foundation for all other distance measurements in the cosmic distance ladder astronomers use. By calibrating other techniques against parallax measurements for nearby stars, astronomers can extend their reach to ever more distant objects throughout the observable universe with increasing reach. Errors in the parallax foundation propagate upward through this ladder, potentially affecting distance estimates to galaxies billions of light-years away and our understanding of cosmic expansion rates. Getting distances right for nearby stars like HD 140283 therefore has implications far beyond just understanding one ancient star's age and history in the galactic halo. The Methuselah star's distance story illustrates a broader lesson about scientific progress, namely that improvements often come gradually through accumulated refinements rather than sudden, dramatic breakthroughs. No single measurement solved the age paradox overnight, but each small improvement in parallax precision, in spectroscopic analysis, contributed to eventual resolution of the puzzle. This patient accumulation of better data is how astronomy typically advances, with generations of researchers building on each other's work toward deeper understanding over decades. The resolution of the Methuselah paradox stands as a testament to this slow but steady approach to uncovering truth about the natural world. As we have seen, knowing the precise distance to HD 140283 was essential for determining its luminosity and therefore constraining its age through evolutionary models. But distance was only one piece of the puzzle, and other refinements in stellar physics were equally important for bringing the numbers into alignment with cosmic chronology. The models astronomers use to calculate stellar ages depend on many parameters, including nuclear reaction rates and chemical abundances that required their own careful revision over time. In the next part, we will explore these refinements in stellar physics and how they contributed to resolving the age paradox that had troubled astronomers for decades. The calculation of a star's age is not a simple measurement, but a complex inference that depends on detailed models of how stars evolve over billions of years. These models incorporate physics, from nuclear reactions in the core to energy, transport through the stellar interior to the behavior of matter under extreme conditions of temperature and pressure. When astronomers found that HD 140283 appeared older than the universe, one possible explanation was that the models themselves contained errors or incomplete physics that skewed the results. Refining these models became a major focus of research in the years following the initial paradox, as scientists sought every source of potential error in their calculations. At the heart of every star lies a nuclear furnace, where hydrogen atoms fuse into helium, releasing energy that keeps the star shining for billions of years. The rate at which these nuclear reactions proceed depends on temperature and density in the core, following quantum mechanical rules that govern particle interactions at subatomic scales. These reaction rates have been measured in laboratory experiments here on Earth, but extrapolating them to stellar conditions involves uncertainties that can affect age calculations significantly. Even small changes in the assumed rates can shift the calculated age by hundreds of millions of years, enough to matter for resolving the Methuselah paradox under investigation. The primary nuclear reaction chain in stars like HD 140283 is the proton-proton chain, which converts hydrogen into helium through a series of intermediate steps involving fusion. Each step in this chain has its own reaction rate, and the overall energy production depends on how these rates combine under stellar core conditions precisely. Laboratory measurements of these rates have improved substantially over the decades, with new experiments providing more accurate values that astronomers can incorporate into their evolutionary models. Updated reaction rates from 21st century experiments contributed to revisions in age estimates for ancient stars, including the Methuselah star, that had puzzled researchers for years. One particularly important reaction involves the production of helium-3 as an intermediate step in the proton-proton chain, and its subsequent fusion into helium-4 as the final product. The rate of this helium-3 fusion reaction affects how quickly the star burns through its hydrogen fuel, directly impacting calculations of stellar lifetime and age. Laboratory measurements of this rate at relevant energies improved significantly in the early 2000s, providing better inputs for stellar models that calculate evolutionary timescales. These updated nuclear physics inputs were incorporated into revised age calculations for HD 140283, contributing to the eventual resolution of the apparent paradox with cosmic age. Beyond nuclear reaction rates, the chemical composition of a star profoundly affects how it evolves, and measuring this composition accurately is essential for precise age determination. For HD 140283, one critical element is oxygen, which affects the opacity of stellar material and therefore how energy flows from the core to the surface of the star. Early abundance measurements suggested the star had a certain oxygen content, but revised spectroscopic analysis indicated a higher abundance than previously thought by a significant margin. This seemingly small change in oxygen abundance had significant consequences for the calculated age, because oxygen affects the star's structure and evolutionary rate in measurable ways. Opacity describes how easily light travels through stellar material, with higher opacity meaning photons are absorbed and re-emitted more frequently on their journey outward from the core. When opacity is higher, energy takes longer to escape from the stellar interior, causing the star to have a different structure than it would with lower opacity material. Oxygen contributes significantly to stellar opacity, so revising the oxygen abundance upward meant recalculating how energy flows through HD 140283's interior and affects its evolution over time. The revised oxygen abundance alone contributed several 100 million years to the reduction in estimated age, a substantial fraction of the adjustment needed to resolve the paradox. The physics of convection also plays a crucial role in stellar evolution models, determining how material mixes within the star and transports energy through bulk motion of gas. In some regions of a star, energy is carried outward, primarily by radiation, with photons bouncing from atom to atom on their journey toward the surface. In other regions, the temperature gradient is steep enough that hot material physically rises while cooler material sinks, creating convective cells that transport energy more efficiently. The boundary between these regions and the efficiency of convection affect stellar structure and evolution, and models must approximate this complex physics with simplified prescriptions for calculations. The mixing length theory is a commonly used approximation for convection in stellar models, characterized by a parameter that describes how far convective bubbles travel before dissipating. This mixing length parameter is calibrated using observations of the Sun and other well-studied stars, but its applicability to ancient metal-poor stars like HD 140,283 inches is less certain. Different choices for the mixing length affect the calculated stellar structure and, therefore, the age derived from fitting evolutionary tracks to observed properties of the star. Researchers explored how sensitive the age of HD 140,283 was to convection assumptions, ensuring that this source of uncertainty was properly accounted for in final estimates. The equation of state, which describes how stellar material responds to changes in temperature and pressure, is another fundamental input to evolutionary models that astronomers use. At the extreme conditions inside stellar cores, matter behaves differently than in everyday experience, requiring sophisticated physics to describe accurately for calculations of stellar structure. Improvements in the equation of state for stellar material, based on better understanding of atomic physics, have accumulated over the years and affected age calculations incrementally. Each refinement brings the models closer to reality, improving the reliability of ages derived for ancient stars like the Methuselah star in our neighborhood of the galaxy. The surface boundary condition, describing how the stellar atmosphere connects to the interior, also influences evolutionary calculations and the ages derived from fitting observed properties. Stellar atmospheres are complex regions where the physics transitions from optically thick interior to optically thin outer layers where photons can escape into space freely. How this transition is modeled affects the predicted surface temperature and luminosity, which in turn affect how well models match observations and what age is derived. Improvements in model atmospheres for metal-poor stars contributed to better matching of HD 140,283's observed spectrum and more reliable age estimates from the evolutionary tracks. The cumulative effect of all these refinements, from nuclear reaction rates to chemical abundances to convection and opacity, was to bring the estimated age of HD 140,283 inches down substantially from its initial impossible value. No single change was responsible for resolving the paradox, but rather the patient accumulation of many small improvements in our understanding of stellar physics over decades. This is typical of how science progresses, with dramatic apparent contradictions often dissolving as measurement precision improves, and theoretical understanding deepens across multiple fronts simultaneously. The Methuselah star paradox was not solved by any revolutionary discovery, but by the gradual refinement of many inputs to stellar age calculations over many years. The collaboration between observers and theorists was essential throughout this process, with new observations motivating theoretical work and improved models guiding new observational campaigns in return. Spectroscopists measuring chemical abundances communicated with modelers incorporating those abundances into evolutionary tracks, while astrometrists refining parallax measurements provided better luminosity constraints for fitting the models. This iterative process continued over years, with each improvement prompting further refinement until the numbers finally converged on consistent values that made physical sense. The resolution of the age paradox stands as a model for how collaborative scientific investigation can resolve apparent contradictions through patient effort and accumulated improvements. As models improved and observational constraints tightened, the estimated age of HD 140283 gradually decreased from the impossible 14.5 billion years toward more reasonable values. By the early 2010s, the best estimates placed the star's age at around 12 to 13 billion years, with uncertainties of roughly 800 million years in either direction. This range finally overlapped with the age of the universe at 13.8 billion years, meaning the star was no longer impossibly old within measurement uncertainties. The paradox had dissolved, not through any dramatic revelation, but through the steady accumulation of better data and improved understanding across multiple areas of stellar physics. The refinement of stellar physics models continues today, with each improvement in our understanding contributing to more accurate ages for ancient stars throughout the galaxy and beyond. New laboratory measurements of nuclear reaction rates, better atomic data for opacity, calculations and improved understanding of convection all contribute to ongoing progress in stellar age determination. The Methuselah star will continue to be studied as techniques improve further, and its age estimate may be refined still more in coming decades of research. For now, though, the paradox has been resolved, and HD 140283 stands as one of the oldest known stars whose age is consistent with our understanding of cosmic history. In the next part, we will examine how the paradox finally dissolved, as all these refinements came together into a coherent picture of an ancient but not impossible star. The resolution of the Methuselah star paradox came not from any single dramatic discovery, but from the patient accumulation of improved measurements and refined models over years. By 2013, a team led by Howard Bond published a comprehensive analysis incorporating the best available data on HD 140283 from multiple sources and techniques. Their work combined the precise Hubble parallax with updated chemical abundances and the latest stellar evolution models to derive a new age estimate for this ancient star. The result was an age of 14.46 billion years, but crucially, with an uncertainty of plus or minus 800 million years. That uncertainty range is essential for understanding why the paradox dissolved, because it means the true age could reasonably be anywhere within a broad span of values. The lower end of the range, 13.66 billion years, is younger than the universe's age of 13.8 billion years by a comfortable margin. Even the central estimate of 14.46 billion years is only slightly older than the cosmic age, and well within one simmer of being consistent. When uncertainties are properly accounted for, the Methuselah star is not impossibly old, but rather pushing the limits of what is possible for stellar age. The concept of uncertainty in scientific measurement is often misunderstood, treated as a flaw rather than an essential part of honest reporting of what we know. All measurements have some degree of imprecision, stemming from limitations of instruments and techniques, and responsible scientists quantify and report this imprecision openly in their work. An age estimate of 14 billion years plus or minus 800 million years is not a failure, but a triumph of careful analysis that acknowledges real limitations. By properly quantifying the uncertainty, the Bond team showed that the apparent paradox was a result of taking earlier point estimates to literally without regard for error bars. Subsequent analyses with updated inputs have continued to refine the age estimate, pushing the central value lower and further from the troubling boundary of cosmic age. Recent work places the Methuselah star's age closer to 12 billion years, though the exact value depends on which stellar evolution models and input physics are used. Even the oldest plausible ages from current analysis remain compatible with the universe being 13.8 billion years old, resolving the original paradox conclusively. The star that once seemed to predate existence is now understood as simply very ancient, one of the oldest objects we can study in detail nearby. The Methuselah star remains remarkable, even with its revised and reduced age estimate, because 12 to 13 billion years is still extraordinarily old by any standard of comparison. This star was already burning steadily when the Milky Way was still taking shape, before our galaxy's spiral arms had formed into their current structure entirely. It witnessed the era when galaxies were merging chaotically and supermassive black holes were growing rapidly, an epoch of cosmic history very different from the present quiet. HD 140283 has survived through approximately 90% of cosmic history, a span of time that defies easy comprehension despite our facility with large numbers. To appreciate this age, consider that our Sun formed only about 4.6 billion years ago from gas enriched by many generations of earlier stellar explosions. When the Methuselah star ignited, our Sun did not exist, and neither did the solar system or the elements that would eventually form Earth and its inhabitants. The iron in your blood and the calcium in your bones were forged in supernovae that exploded after HD 140283 was already ancient by most standards. This star has been burning steadily since before the raw materials, for human existence had even been created in stellar furnaces throughout the galaxy. The resolution of the age paradox teaches important lessons about the nature of scientific inquiry and the way apparent contradictions are addressed through careful investigation over time. Scientists did not dismiss the impossible age as obviously wrong and ignore it, nor did they accept it and conclude the universe's age must be revised upward. Instead, they took the discrepancy seriously as a puzzle worthy of investigation, examining every assumption and measurement for possible sources of error systematically. This approach exemplifies the scientific method at its best, neither dogmatic nor credulous, but genuinely curious and willing to follow evidence wherever it leads through patient work. The collaborative nature of the resolution is also noteworthy, involving specialists from many different areas of astronomy and physics contributing their expertise to the problem. Astrometrists provided precise parallax measurements, while spectroscopists analyzed chemical abundances with increasing accuracy, and both groups communicated with theorists modeling stellar evolution and interior physics. Nuclear physicists contributed updated reaction rates from laboratory experiments, while atomic physicists provided better opacity data for modeling energy transport through stellar material accurately. No single researcher or team could have resolved the paradox alone, but together they assembled the pieces needed to understand this ancient star properly at last. The willingness to hold conclusions lightly while awaiting better data is a virtue that the Methuselah star story illustrates beautifully for anyone studying scientific method and practice. For years, astronomers knew the 14.5 billion year age was problematic, but they did not prematurely declare it wrong without evidence pointing to specific errors. They continued gathering data and refining techniques, confident that the contradiction would eventually yield to patient investigation as understanding improved incrementally over time. This patience, so different from the demand for immediate answers that characterizes much of modern life, is essential for genuine scientific progress on difficult problems. The Methuselah star also illustrates the importance of uncertainty quantification, a sometimes underappreciated aspect of scientific reporting that proved crucial for resolving this particular paradox. Early age estimates often reported central values without adequately conveying the range of plausible values consistent with measurement and modeling uncertainties in the calculations. When full uncertainties were properly propagated through the analysis, what seemed like an impossible result became merely a very old star at the edge of plausibility. Scientists now emphasize reporting uncertainties clearly, precisely, because of cases like this, where point estimates can mislead without the context of error bars providing perspective. The paradox dissolution also reinforces confidence in our understanding of cosmic age, derived from completely independent methods, including the cosmic microwave background radiation measurement. If the Methuselah star had truly been 14.5 billion years old, with no plausible path to reducing that age, cosmologists would have faced difficult questions about everything. The fact that refined stellar ages converge toward consistency with cosmic age suggests our basic framework for understanding the universe's history is sound. Multiple independent lines of evidence pointing to the same cosmic age is exactly what we expect if our scientific understanding is correct and complete. HD 140283 has transitioned from a paradoxical puzzle to a valuable laboratory for studying ancient stellar populations and the conditions of the early universe itself. Its very existence so close to us is fortunate, providing a nearby example of the kind of star that formed in the universe's first billion years or so. More distant ancient stars are harder to study in detail, so having the Methuselah star at only 200 light-years gives astronomers exceptional access to examine. The techniques refined during the investigation of its age paradox now benefit the study of other ancient objects throughout the galaxy and in neighboring systems. The scientific community's handling of the Methuselah star paradox demonstrates how apparent contradictions can drive progress, rather than undermining confidence in the scientific enterprise as a whole. A star that seemed older than the universe was not swept under the rug or used to discredit established cosmology, but treated as a puzzle to be solved. The resolution came through the normal workings of science, with better data and improved models, eventually bringing everything into alignment without revolutionary upheaval. This patient, cumulative approach to resolving contradictions is less dramatic than paradigm shifts, but represents how most scientific progress actually occurs in practice over time. As the paradox faded away, what remained was a deeper appreciation for this remarkable ancient star and what it can teach us about cosmic history preserved in starlight. In the final part, we will reflect on what stars like HD 140273 reveal about the early universe and our place in the vast timeline of cosmic existence. The Methuselah star has been burning steadily for approximately 12 to 13 billion years, carrying with it information from an era we can access no other way. In its spectral lines and chemical abundances, we read the story of the early universe, a time when heavy elements were scarce and stars were just beginning to form. This ancient sun is a messenger from cosmic dawn, a survivor that has persisted through nearly all of cosmic history since the beginning of time. Contemplating its existence invites a kind of quiet wonder at the vast timescales that govern the universe we inhabit, as brief visitors in cosmic terms. The light we receive from HD 140283 tonight departed the star about 200 years ago, around the time Beethoven composed his late symphonies in early 19th century. But that light carries information far older, encoded in the chemical elements that were present when the star formed over 12 billion years before those photons began their journey. In this sense, we are receiving a message from the deep, past a record of cosmic conditions preserved in the spectrum of an ancient sun. The star itself is a time capsule, and reading its light opens a window onto an epoch otherwise beyond our direct reach of observation. Ancient stars, like the Methuselah star, are the primary tools we have for understanding what the universe was like in its first billion years after the Big Bang. The cosmic microwave background tells us about conditions at 380,000 years after the beginning, when the universe first became transparent to light. But between then and when the first galaxies became visible, a period called the Cosmic Dark Ages elapsed that we cannot observe directly with current technology. Stars born in that early era, if any survive, carry information about conditions we can probe in no other way, making them priceless for cosmology research. HD 140283 formed somewhat after the cosmic dark ages ended, but still in an era when the universe was very different from its present state entirely. The galaxies we see today had not yet assembled into their current forms, and the chemical enrichment from stellar explosions was just beginning to accumulate in interstellar space. The star's low metallicity reflects this early environment, with heavy elements at only a fraction of a percent of the abundances found in our sun today. By studying stars like this one, astronomers can reconstruct conditions during the first epoch of galaxy formation, learning how the universe evolved from primordial simplicity to present complexity. The field dedicated to studying these ancient stellar survivors is sometimes called stellar archaeology, drawing an analogy to how human archaeologists study artifacts from past civilizations and cultures. Just as a pottery shard or stone tool can reveal information about the people who made it long ago, an ancient star's spectrum reveals conditions in the early universe. The chemical abundances in HD 140283 tell us about the supernovae that enriched its birth cloud, constraining models of the first stellar generations that lived and died before. This forensic approach to astronomy extracts remarkable information from objects that have persisted for billions of years, silent witnesses to cosmic history, spanning almost all of time. The search for even more ancient stars continues, with astronomers hoping to find survivors from the very first generation of stars, the hypothetical population 3 that has never been observed. These first stars, if any, survive at low masses, would contain essentially no elements heavier than lithium, the primordial composition from Big Bang nucleosynthesis alone. No such star has yet been found, possibly because the first generation formed only with high masses that burned out quickly and left no survivors to the present day. But the search continues, and each ancient metal-poor star discovered adds to our understanding of the early universe and its initial stellar inhabitants that began cosmic evolution. HD 140283 and stars like it teach us that the universe has a history, a story that unfolded over billions of years before Earth existed or could have observers. This history is not merely an abstract timeline, but is recorded in physical objects that persist to the present, carrying their ancient origins with them across the eons. The atoms in the Methuselah star were forged in the Big Bang. Itself, hydrogen and helium assembled into a star in the early universe when everything was young. Those same atoms are still there, still undergoing fusion in the stellar core, still shining their light toward us across 200 light-years of intervening space. There is something profound about receiving light from an object that has existed for such an unimaginable span of time, witnessing nearly all of cosmic history unfold. Human civilization is perhaps 10,000 years old, a mere instant compared to the 12 billion years the Methuselah star has been burning steadily without interruption. Our entire species, Homo sapiens, has existed for only about 300,000 years, still just a flicker against the star's ancient persistence through the ages. When we observe HD 140283, we are glimpsing something that has endured for 40,000 times longer than humans have existed on our small planet. This perspective can be humbling, but it can also be strangely comforting, placing our brief concerns against a backdrop of vast cosmic timescales that dwarf everything. The Methuselah star knows nothing of human worries or ambitions, burning steadily, as it has for billions of years, indifferent to the brief dramas that occupy our attention. It will continue burning for billions of years more, long after our individual lives and perhaps our entire civilization have run their course on Earth. Against such timescales, the urgencies that fill our days seem smaller, more manageable, less absolute in their demands for immediate attention and constant concern. The study of cosmic time also connects us to something larger than ourselves, linking present observers to past and future generations of curious minds seeking understanding. The astronomers who first noticed HD 140283's unusual motion over a century ago could not have imagined the precision measurements we make today with space telescopes orbiting Earth. And future astronomers will surely refine our understanding further, with techniques and instruments we cannot yet imagine, continuing the work of decoding this ancient messenger. Science is a multi-generational project, with each era building on what came before and laying foundations for what will come after in centuries to follow. The Methuselah star paradox, now resolved, stands as a reminder that apparent contradictions in science are often invitations to deeper understanding rather than crises requiring abandonment of frameworks. The universe is not obligated to be simple or to yield its secrets immediately, and some puzzles take decades of patient work to resolve satisfactorily. This patience, so characteristic of astronomical research, offers a model for approaching complexity in other domains, trusting that careful, persistent effort will eventually bring clarity to confusion. The contradiction between the star's age and the cosmic age was not a failure of science, but a challenge that inspired decades of fruitful research. As we come to the end of this exploration, the Methuselah star continues its ancient journey through the galaxy, utterly unaware of our attention and interest in its remarkable history. It has passed through our cosmic neighborhood before and will again, tracing its long elliptical orbit through the halo far above and below the galactic plane. For a cosmic moment, we have the privilege of studying this ancient wanderer, learning what we can before it moves on to other regions of the galaxy. The photons we gather tonight will be replaced by fresh ones tomorrow, an endless stream of light from a patient ancient source in Libra. The universe is old, and some of its oldest objects are close, enough for us to study in remarkable detail, messengers from an era we cannot otherwise access. HD 140. 283, the Methuselah star once seemed impossible. A star older than the universe that contains it. A logical contradiction demanding explanation and resolution. Through years of patient work, astronomers resolved the paradox, demonstrating that better measurements and improved models could bring apparent contradictions into harmony with each other. What remains is wonder at a star that has burned for 12 billion years, at a universe that allows such persistence and rewards such patient inquiry. The light from ancient stars falls gently on our world tonight, as it has for all of human history and long before we existed to notice its arrival. These photons carry stories from cosmic dawn, encoded in wavelengths and absorption lines that patient astronomers have learned to read, like ancient scripts from distant times. The Methuselah star is one voice in this cosmic chorus, a survivor from the universe's youth that speaks quietly to anyone willing to listen with sensitive instruments. And in listening, we find ourselves connected to something vast and ancient, humbled by timescales we cannot truly comprehend, but strangely comforted by the perspective they provide. The night deepens and the stars continue their ancient journeys across the sky, indifferent to our observation, but somehow more meaningful for our awareness of what they represent. HD 140. 283 will rise and set with the seasons, a faint point of light in Libra that holds within it stories from the beginning of cosmic time. The paradox has dissolved, the questions have found their answers for now, and the ancient star burns on through the quiet darkness of interstellar space. And we, brief visitors in a vast old cosmos, have had the privilege of contemplating its light and learning something of its remarkable history across the ages. This concludes our exploration of the Methuselah star and the paradox of an object that once seemed older than the universe, now understood as simply ancient, beyond easy comprehension. Thank you for joining this quiet journey through cosmic time. And may the vast perspectives of astronomy bring the same peaceful clarity they have offered to stargazers throughout human history. The universe is patient, and so too can we be, resting in the knowledge that some questions yield their answers only to those willing to wait. Until next time, may the ancient light of distant suns accompany your thoughts gently into stillness, as it has for observers across countless generations before us.